Last time, what we studied was the asymptotic symmetry group, the Bondi-Meissner-Sachs group, which is tailored to null infinity, and therefore for gravitational waves. And let me just summarize. And then after that, I would like you to ask any questions you may have before we go to the next topic. So the summary is basically that we need the notion of asymptotic flatness at null infinity to talk about gravitational waves in nonlinear general relativity. And the asymptotic symmetry group, called the Bondi-Meissner-Sachs group, is the subgroup of the diffeomorphism group of Scri, which preserves the universal structure. A universal structure we need, the structure that is common to all asymptotic flat spacetimes. Although I did not show this, this group can also be obtained as a quotient. You take the physical spacetime and you consider all diffeomorphisms on this M tilde, which preserve the asymptotically flat boundary conditions, and you divide it by, or take the quotient of this group by a normal subgroup, which is a subgroup of those diffeomorphisms which don't do anything at infinity, which are asymptotically identity at infinity. So in terms of Scri, they don't do anything at all at Scri, whereas these ones can be acting non-trivially on Scri, but they preserve the boundary conditions. So there are two ways of getting this group, and we obtained one using the conformal completed spacetime. And we saw that this group has a structure of what is called semi-direct product with an abelian, a commutative infinity-dimensional group, which is a normal subgroup of what we call as super translations, and they are generated by vector fields of the type f of theta phi times n. In other words, f is actually Lie dragged by n. So it only depends on the angles. And under the changes of the conformal factor, Na changes to omega to the -1 times Na, and therefore f actually changes. So therefore one says that it has a conformal weight plus 1 because f changes by omega. N has conformal weight -1, and f has conformal weight 1 because C should not care about which conformal factor you choose. And then furthermore, the super translations admit a 4-dimensional canonical group of translations. And if you go to a Bondi conformal frame, which means that the metric is a unit around two-sphere metric, then these, if you take the functions, instead of taking general functions of theta and phi, if you just take linear combinations of the first 4 YLMs, so Y00 plus Y1M, then you obtain a subgroup, and that is called the translation subgroup, and that is going to be very useful to define the linear momentum. So I think I did not have this in the notes are circulated. So I just wanted to tell everybody that further discussion of the enlargement of the Poincare group to the BMS group due to super translations is given in this appendix of this paper. If you like, you can just copy down 1906.00913. Okay, so this is where we are. And now what we would like to do is to understand if you have any questions. If there are questions on the BMS group, please ask now. If there are no questions, I will continue. The main point is that we're going to have these asymptotic symmetries, and then we've got various fields at Sky, and we're going to use them together to talk about fluxes of energy, fluxes of momentum, angular momentum carried away by gravitational waves. Okay, so any questions? You can either speak or you can type the message in the chat box. Okay, so there are no questions. So let us just let us just go. Let us just go to the next topic. Oops, sorry. I'm sorry about that. So now this is lecture number 4. And now what we want to do, I would like to show you how you can use this flux, the Mesner-Sachs group to talk about Bondi-Mesner-Sachs energy momentum and supermomentum. And this is what I would like now to do. But let me just begin with an introduction to something that you already know, which has to do with the Maxwell theory. By the way, I'm always talking about Maxwell theory because that is a theory that you are most familiar with. But everything I say is also holds for Yang-Mills series and also for the scalar fields in Minkowski space-time. So Maxwell field is just taken as a concrete example. So in the Maxwell case, the statement is that if you give me any Killing vector field, Ka, in Minkowski space-time, then I can take, given any solution, FAB, I can construct the stress energy tensor of that solution. So TAB is just given by FAM, FBM, minus a trace. So if like minus its trace. This is the stress energy tensor of the Maxwell field. And now we know that this is the conserved quantity. So if K, for example, is a time translation, then this would be the energy. If K is a space translation, then this flux up here, this quantity up here, would be the 3 momentum. If K were rotation, then this would be angular momentum. So here's a picture that we can look at. And what we are doing is the following. We are looking at this Minkowski space with completion. This is Sky plus, Sky minus, and Sky plus here up here. And the statement is that I can consider, for example, a T equal to constant surface, T equal to constant, say T equal to 0 surface, and I calculate this. Or I can consider T equal to T naught surface. So this is T equal to T naught. And I calculate this quantity. And then the statement is that because stress energy is divergence free, and the Killing vector field satisfies the Killing equation, this implies that the quantity calculated here is equal to the quantity calculated here. And this is a later time surface. It all these surfaces go through I naught. So, and then the statement is that I got one T equal to constant surface, another T equal to constant surface, another T equal to constant surface, another T equal to constant surface. And as T goes to infinity, these surfaces, T equal to constant surface, in this picture would reach scrap. So this, taking this limit, T going to infinity, T naught going to infinity, so T naught is equal to constant, I obtain, instead of this surface, I obtain scry, and then I just obtain, it is a fact, you can check there is an exercise, I obtain a function of theta and phi, which is the translation. So the Killing vector field becomes alpha, which is a translation function up here that I just mentioned, which is a linear combination of the first 4 YLMs times the vector field NA, and NA is just the normal vector field here, NA. And then we just obtain this formula that we had seen before, and I had discussed this already before, that you obtain such a formula for if K is equal to translation up here. And therefore, this is the energy. If you take K to be equal to just NA, alpha equal to 1, that will be a time translation. And then this formula would, so alpha equal to 1. So this is just 1 up here, 1 up here. So therefore, we just left with 5 to naught squared. And that is the energy carried by the electromagnetic waves across scrap. So this constant quantity you can think of as being the flux through any surface. You can just call it energy, but you can also talk about it as energy, flux of energy through any surface. And the flux of energy through this surface is the same as the flux of energy through this surface, is the same as the flux of energy across Gram. So we needed two things. We needed a stress energy tensor. I mean, given a solution, we needed a stress energy tensor, and we also need a symmetry. Now, in full general relativity, we do not have Killing vectors, but as we saw, we do have asymptotic symmetries at Scri. These symmetries exist at Scri up here. For example, if f of c equal to f of theta and phi times na, where f is arbitrary, that's a super translation. And if it is the first four YLMs, then it is a spherical harmonics, then it is a translation. But we do not have a gauge invariant notion of stress energy tensor for the gravitational field. And as somebody asked me early on, this is, I mean, it's also the case that this just shows that we do not have a local notion of energy or energy flux in general relativity. Now, the statement is that what we can do is, we have this difficulty, but we can, the nice thing is that in Maxwell theory already, we have got this answer which came from the stress energy tensor, and then we took the limit. But this answer can be also obtained by a completely different method. And that different method, the same expression can be obtained using Hamiltonian methods. So f is, of course, a function of the Maxwell field, because this quantity here would just be equal to, the stress energy tensor would be equal to FAM, FBM times GMN times Ka times unit normal to the surface times D3x. I'm just integrating this. This flux quantity is just equal to that. Okay, so I'm just calculating this quantity. So this flux quantity up here. But this quantity can be obtained by constructing a phase space for the Maxwell field with the configuration variable, momentum variable, and then noticing that the Poincare group generates motions on this phase space. It induces canonical transformations of this phase space. In terms of solutions, if you give me a solution and if you give me a Killing vector field, then if F is a solution, then you can check quickly that in fact this is also a solution. So you can check that this is also a solution. So this is a nice exercise for you to do. And similarly, previously, this is something that I had already given you as an exercise to do. But I would again say, if you're not done it, then please do this exercise. So the statement is that given a Killing vector field, I can take the lead derivative by that vector field of a solution, and I again get a solution. And therefore, on the space of solutions, actually I got a Poisson bracket structure, and the canonical and this actually preserves the Poisson bracket, and therefore I can ask for the generating function which generates this canonical transformation. F goes to the KFF, and this turns out to be precisely this quantity up here. Therefore, we can say that, oh, I don't really need the stress energy tensor to talk about the total energy flux across any surface, either this surface, total energy flux across either this surface or this surface. I do not need that. What I would need is just a Hamiltonian methods. So maybe we can use these Hamiltonian methods also in general relativity. And interestingly, this is true. In fact, many of you may be already familiar with this in the context of spatial infinity. So in spatial infinity case, what we do is we take a three-dimensional manifold, it's called sigma. Think of it as a t equal to constant surface, t equal to 0 surface up here. And we often consider the intrinsic metric here, HAB, and the extrinsic curvature here, KAB. And we can construct a phase space of this initial data. And then the statement is that you can construct Hamiltonians on this phase space. And these Hamiltonians, in fact, give you the ADM or the Aronovitch-Dazer-Misner 4 momentum. You must have seen the definition of the ADM energy, ADM momentum. The famous positive energy theorem says the ADM energy is positive and so on. And those actually were obtained using the Hamiltonian methods the first time. And now what we can do is we can generalize this to this particular ADM for momentum is a total for momentum of the solution. It includes both the sources and radiation. So in this picture up here, if you have some sources up here which are radiating, then the ADM for momentum obtained at spatial infinity at I0, that is a total energy and total momentum. It includes the contribution to the sources, contribution to radiation, everything. But now what we are interested is really null infinity. And at null infinity, we will just get the form momentum that is carried away by gravitational field, by gravitational waves or electromagnetic waves, etc. So this is really the null infinity. So we can do the phase space of radiative modes at null infinity. The phase space was discussed in this paper, and the Hamiltonians were calculated in this particular paper. So we're not going to do the details. I just want to tell you what the basic ideas are and then what the results are. But I want to emphasize that this is really a very beautiful mathematical structure. If some of you are more mathematical physics oriented, then you will really enjoy this very beautiful interplay between geometry and physics up here. And the phase space of radiative modes for general relativity is very similar to the phase space of radiative modes for the Maxwell theory and for Yang-Mills theory. So this is now what I want to explain. So what we are going to do is to take an asymptotically flat solution G tilde AB in the inside, and we conformally complete it and obtain the conformal completed manifold and the metric GAB. So GAB is conformally completed. G tilde AB is a physical metric, which is the solution to Einstein's equation. And now if I given such a structure, I look at scrap. And what we saw already is that there is a universal structure. There's a structure which is shared by all asymptotically flat metrics. And that structure is really the space of Q and N. And so we'll just call it the zeroth order structure, because this structure is induced at scri just by the metric GAB at scri. If you give me the metric GAB at scri, then I can calculate the QAB. This is the intrinsic metric, because QAB is just the pullback of GAB. And I can also calculate NA, because NA is just equal to GAB times grad B omega. This is sort of free. If you give the omega, then I can take its gradient. I don't need any metric or anything like that. And then I'm just looking at raising its index. So this is therefore zeroth order structure in the sense that it comes directly from the metric. But in the conformally completed space-time, we have metric, but we also have a derivative operator, which is compatible with the metric and is torsion-free. And this derivative operator, or sometimes it is called connection, this is like the vector potential in Yang-Mills theory or in Maxwell theory. And it turns out that this derivative operator that we got this is a four-dimensional quantity, four-dimensional derivative operator. It turns out that that four-dimensional derivative operator actually induces just on scri. So you can just look at the boundary and forget about the interior. If I do that, just looking at scri, then on scri, I obtain a derivative operator on the three-dimensional manifold scri. I obtain an intrinsic derivative operator as follows. Supposing you give me a certain vector or co-vector here, K on scri, then what I would like to do is to define what is dA of KB. So the prescription is that given this black object, which is living on scri, KB, you just extend it in the space-time any way you want in a smooth manner. And then once you extend it in the space-time in any smooth manner, I can calculate grad A KB in the little neighborhood of null infinity. I can calculate this quantity, grad A KB. And then finally, what I do is I pull this back to, so this two tensor with two indices. It has covariant indices, so I can pull back to scri. Again, pull back just means that I just look at this tensor and I allow myself, let me write it better. I look at this tensor and I allow myself only to put vectors V and W, which are tangential to scribe. So pullback has information only about the part of the tensor which acts on vectors which are tangential to scribe. Grad A KB, I can act on it on the vector L, for example, LA, LB, I can do that, or LA, VB, I can do that. Whereas on the pullback, I only can act by NA, MA, and M bar A. So if I take pullback grad A KB, then the contraction of A and B can be done only with these vectors, which are always tangential to scribe. That is what pullback means. So you take any extension of the given K to the extension is denoted in blue here. The K that is given on scribe is in black. You take any old extension, take the derivative, and then pull back. And the interesting thing is that you might say, in general, if you just do it on any submanifold like that, then in general, of course, this answer that you get will depend on how you extend K to the space-time. But it turns out that because grad A and B is equal to 0, because the null normal to scribe satisfies this condition, this particular pullback that I got here is completely independent of the extension K, the blue K that I have done of what is given to me on K. And therefore, this object is completely well defined on scribe, and that thus, because grad A and B is equal to 0, the derivative operator grad that I have got induces a connection or a derivative operator D on the intrinsic manifold scribe here. And now, because the derivative operator in space-time is compatible with the metric, it follows that the D is compatible with the metric Q up here. Because I just pull back this equation, pull back of G is equal to just Q, and pull back of grad is just D. And therefore, if I just pull back this equation, I just get this equation up here. And we know that grad A and B is equal to 0 on scribe. That is the equation that that is satisfied in the completed space-time. And therefore, if I pull back this index N, and N is already tangential to scribe, then the statement is that I get dA and B equal to 0. So the given derivative operator in physical in the conformal completed space-time gives me a derivative operator on the boundary up here. Now one might say that, oh, so now just like the derivative operator operating on G is unique, I'm looking at torsion-free derivative operators. It is unique because the metric compatibility gives me a unique derivative operator. What about here? Well, here this D is not unique because this is not a metric. It's not a non-degenerate metric. It is degenerate along this direction up here. If it were a non-degenerate metric, then D would be unique and would be finished. But it is not the case. So there are many Ds which will actually kill Q and will also kill N up here. So D is not unique, and it carries further information which is not captured just by which is not captured in N and Q. It is not captured here. It has more information. And this is a fact. And again, the references I will give explains this in some detail. But this D can therefore vary from one physical space-time to another. For example, if G tilde AB were Schwarzschild, then on the D that I will obtain, I will get one answer. If this were a radiating space-time, then I will get would be a different D. But for all these space-times, the N that I get and the Q that I get are the same. The Q and N are the same, but D is different. And all these Ds will kill Q, will kill N, but still they are different from each other. And this is really the important point, that it turns out that this freedom is critical because these Ds carry precisely the radiative information. There's a very non-trivial interplay between physics and geometry, and this is shared by Young-Mills fields, by Young-Mills gauge theories, as well as by, of course, in particular by Maxwell theory. So the point is basically that we got universal structure, which is Q and N, But given a space-time or given a conformal completion of the space-time, I also obtain a derivative operator on Scri, and this derivative operator is our object of most interest. The new information, as I said, in D varies from one space-time to another. Now we want to extract this information. We want to know what is this information. So what we do is the following. We look at this Scri up here. I mean, the derivative operator exists without any further structure. But in order to extract the information in some familiar terms, we're introducing the extra structure. The extra structure is not necessary to define D by itself, but it is necessary to understand how much information there is in D. So what we do is the following. We can take a cross-section of Scri and call it U equal to U naught. We had done that before. And then define a coordinate U by just asking NA grad A of U is equal to 1 and U is equal to U naught on this cross-section. That defines U on Scri because you do it on every generator of Scri. And therefore, I get a coordinate U on Scri. So given any cross-section, we set U equal to U naught and then ln of U is equal to 1 or NA grad A U equal to 1. Therefore, we get a coordinate U, and then we acquire a one parameter family of cross-section U equal to constant. Because U equal to U naught, I'll get U equal to U1, U equal to U2, etc., etc. And now what we can do is we can look at the normal to these cross-sections. And the normal to this cross-section is vector L that we talked about here. Or in terms of covectors, what we can do is the following. If I look at the covectors up here, HA, in terms of the covectors up here, so we can call these covectors horizontal if they're perpendicular to n. That is why we call them horizontal. And they're also lead drag by n. So these covectors, if you like, remain the same along the generators of Scri. HA remain the same. So now the point is that the action of, because D kills Q, so in the angular directions, the action is completely determined. So the action of D is completely determined by df q equal to 0. So there's new. All the derivative operators will agree on their action on the horizontal one forms. So this is something that is non-trivial, but all the derivative operators which are compatible with the metric up here will actually have the same action. But what can vary from one solution to another is really the action on the other object, and the other object is this L. Or if you like, this D, the L is the same as downstairs L is the same as D of V. Okay, so basically in the d theta direction and d phi direction, we know what D does, but we don't know what D does in the du direction or in the du direction. That's what we don't know. So this L is really covector. As a covector, it is just equal to dA of U. As a vector, it looks like that, but as a covector, it is just dA of U. And now the statement is that the new information in D, which changes from one space-time to another, is encoded in a quantity called shear, which we have seen before. And what you do is you take the derivative of this L, and L you can just take it to be equal to dA of U. You can take this L and you can take the derivative and you can project both these indices and into the two sphere up here. So I'm taking derivative of L, projecting these indices, and then I just take, which is the same as just pulling back grad A of L and taking its trace-free part. TF just means trace-free part. So it is the same as just calculating df LB. L is df of U. So L is really intrinsically defined on Scri up here because U, theta, phi are coordinates. Therefore, du, d theta, d phi are defined intrinsically on Scri. And therefore, dA of U is also defined intrinsically on Scri. So you just take dA LU, and then you're just taking the trace-free part of that. So to summarize, because it is the case that d of q is equal to 0, The action of D on the horizontal one forms is completely universal. It is the same for all horizontal V form. So the action of, it is the same for all D. Given any horizontal wave form, every D which kills the metric will have the same action. But does not have the same action on the normal one form. And the normal one form to this is U equal to constant. And therefore the normal one form is just given by LA, which is dA of U. This is normal one form within Scalar, because the cross section is U equal to constant. Okay. So I got this constant U equal to constant cross section, and we got this normal one form up here. So the statement is that the new information in D is a shear, and it is really just a trace-free part of this normal one form. Now, a few lectures, just not the last lecture, but the lecture before that, we defined the quantity called shear, and which is really we're taking this sigma naught, sigma AB, and contracting it to 2 m's. So this is really horizontal, it is pulled back. So sigma AB and B equal to 0. Therefore, it only has M and M bar components, and therefore sigma naught MA MB times 6 sigma naught AB. Those are the two components of the transverse trace-free sigma naught AB. Sigma naught AB is transverse and trace-free. It is trace-free by construction. It is transverse because this is equal to 0. And therefore, it is only two components. And we had seen last time that if I were to contract with M and M, then I just get H plus I H cross, which is the waveform. Or in the physical space-time, you're taking transverse traceless HAB and contracting with MAMB and taking the limit as we go to scribe. Thus, the information in D that is not universal or kinematical, that can vary from one space-time to another space-time, one solution of Einstein to another solution of Einstein, is precisely this D, but the D is really completely the same as its information is same as the sigma naught, and sigma naught information is the same as the waveform. So it's very beautiful that the waveform is precisely the information that is contained in D, which changes from one space-time to another. It is not universal. And the radiative phase space, as in the references I will give you, is all built from these derivative operators. Or if you like, you can coordinatize it by sigma or by the waveform. And these derivative operators just satisfy these two equations. So there are infinitely many derivative operators which satisfy these two equations because Q is degenerate, and the information in an individual Q, in individual D, which satisfy this equation, is all contained in the waveform. Now recall that the News tensor was just 2 times ln of sigma, or the News, the function up here, NA, this is just given by, N is given by sigma dot. So therefore, the statement is that the News can be constructed completely from this derivative operator or from the phase space variable sigma that we got. And then we got this pullback of KEB. This was the radiation field, which had information of psi 4 naught. And pullback, I called it as EAB for electric part. And that was given by 1/2 times time derivative of, or LN of the News. And therefore, if I plug into it M bar A, M bar B, I get here a psi 4 naught. And therefore, psi 4 naught is a time derivative of News, or a second time derivative of the shear or the waveform. So shear is the same as the waveform, as we just saw up here. So therefore, shear of the waveform is a second potential for the radiation field. And this fact is heavily used in the numerical relativity and the waveforms. What LIGO detects is really this waveform. So this is the waveform that LIGO detects. So if it detects, if you like, this shear, sigma that we got up here, because the information in the waveform is the same as the shear. And the shear, if you like, is a coordinate way of talking about, a concrete way of talking about the derivative operator. So literally, LIGO is detecting these various derivative operators. Various different waveforms created by black hole collisions, neutron star collisions are all different Ds or different waveforms, and that is what LIGO detectors pick up. So to summarize, at null infinity, we have a symmetry group B. that preserves the universal or the kinematical structure that is common to all asymptotically flat space-time. In our analogy of the Maxwell field, this B, in the Maxwell case, the analogous object is a Poincare group. That is what we have. And now we've got a dynamical field, and the dynamical field is this D, and the dynamical field in the Maxwell case is this FAB. And now what we see is, in the Maxwell case, we saw that I can take FAB goes to FAB plus little change, which is just decay of FAB, infinitesimal motion. This infinitesimal motion is a canonical transformation, and its generating function is the Hamiltonian, if you like, is precisely the flux of K, of the quantity associated with K. If K is a time translation, the flux of energy, space translation is a flux of momentum, and so on. So now, coming back to the dynamical field D up here, it is really, you think of this D as the analog of FAB. And the statement is that if you change your space-time, then D changes. Is a potential for the bonding news and a second potential for the radiation field, and it varies therefore from one space-time to another. If you are in the stationary space-time, the D is trivial because it is completely determined by the metric QAB. That is to say, we can always choose U equal to constant cross sections such that they are shear free. The shear vanishes. If that is to say, the waveform vanishes. I mean, we know that in stationary space-times, there are no gravitational waves, therefore the waveform at Scri must vanish, and that is indeed the case. And again, sigma is equal to 0 means that the news is equal to 0, and it means psi 4 is equal to 0, because as we just saw, sigma news is given by sigma dot, and psi 4 is given by sigma bar double dot. And therefore, if sigma is equal to all these quantities are 0, and there is no gravitational waves. But in radiative space-time, we've got a different structure. The D has now non-trivial information. NAB is not equal to 0, psi 4 is not equal to 0, shear is not equal to 0. You cannot find cross sections such that shear is 0 everywhere on Scri. So we got this dynamical field, and we got symmetries. So we got symmetries and we got dynamical field. Now we put them together, and we are going to obtain the fluxes. As Hamiltonians, we generate canonical transformations. So using the BMS symmetries of psi, these are the symmetries, and radiative phase space, we can compute the fluxes carried by gravitational waves across Scri, exactly like in Maxwell theory. The Hamiltonians generated the infinitesimal canonical transformation. The infinitesimal canonical transformation is that D goes to D plus epsilon times lead C of D. What do I mean by that, lead C of D? Well, that means if you give me any K on Scri, I can calculate dA KB, and that goes to dA KB plus epsilon times lead C of dA KB minus dA of lead C of KB. So because I'm subtracting lead C of KB up here, this difference that I got here is only about lead C of dA. So this is an action of the BMS group on the derivative operators on the radiative phase space, and exactly what happened for Maxwell theory, Young scalar fields. The action was always FAB goes to FAB plus epsilon Lee K, where K is a killing vector field of FAB. This was the canonical transformation, and we obtained the Hamiltonian, which generates it. We now have a canonical transformation because we got symmetries, and therefore we can ask for the fluxes. And then what we find is the following: if we take a super translation, if C is equal to F times NA, then the flux is just given by, you calculate it, and again, I give references for this, is given by 1/32 pi g times du d2s times the function of theta and phi that we got here. This is a conformally weighted function, times NAB, and this is the news, and contracted with NAB plus dA dB of F. So this is an extra term that you get up here. And this is in a Bondi conformal frame. where the metric QAB has constant scalar curvature equal to 2, or it is QAB is a unit to sphere metric. So in such a boundary conformal frame, for simplicity, and you can write down the general formula, it's just a little more complicated. So let me just, I just did this simplification. And furthermore, you can isolate translations. These are super translation. F is any function of theta and phi. It has conformal weight. It is any function of theta and phi, but under the transformation that we got. So let me start again. So if I make QAB goes to omega squared QAB, and NA goes to omega to the minus 1 NA, then F goes to omega times F. So that F times NA, which is CA, does not depend on the choice of conformal factor. It is physically invariant. So in this case, F is a conformally weighted object, but du also changes. If NA goes to omega to the minus NA, then du also changes, and you can quickly check that in fact these two factors, the conformal behavior of these two factors is such that this quantity is really conformally invariant. So I can evaluate it using any conformal factor, and we just choose the boundary conformal factor just to make formulae shorter. And now if you look at translations in the boundary conformal factor, this F is given by alpha times n, where alphas are linear combinations. These are just the numbers. Alpha is real, and so this combination should all be such that alpha is real. Where alpha naught, if you like, is just a y00, which is a constant, and then alpha m are constants, and y1m, not ylm, but ynm. So m is just going from 1 to 3. So m is going from 1 to 3, and this alpha naught is a constant. So I got a 4-parameter family, and these are the translations in Minkowski in asymptotically flat space time that correspond to the translational Killing vector field in Minkowski space. In Minkowski space, if you look at translational Killing fields in the space-time interior, and you take the limit to Scri, then you get precisely these objects. So if I go from here to here, then some simplification occurs, namely that here I got dA/dBF, which is a general tensor field. But if these are one-year combinations of the y1s, then you can check easily that this is just spherical harmonics. So you can check it very, very easily that this object dA/dBm, dA/dB of alpha, is in fact proportional to the metric itself. It is something times the metric itself. So therefore, this factor is going to be proportional to the metric, but n is trace-free. So NAB times this factor goes away. Therefore, the second term just goes away in the case of translations, and you just obtain alpha. Instead of F, I get alpha times NAB. So to get energy flux, you set alpha equal to 1. And then the energy flux is given by du, the same thing, times this equal to 1, and I get NAB, because this term is 0. Actually, in this case, F is just equal to 1. Therefore, this is just going to go away. So I'll just get NAB. And this is a positive quantity, because I just can't the same thing twice. And we know that this is the metric on Scri has signature 0 plus plus. So there is no minus. Therefore, this is a positive quantity. And this just says that means that the flux of gravitational waves across Scri. So if I got some binary system emitting gravitational waves across Scri, then the flux of across Scri of this energy is just given by this formula. And we see that even locally, this energy is positive. And this is a gauge invariant statement, doesn't depend on coordinates, doesn't depend on tetrads, doesn't depend on the conformal factor, because everything is conformally invariant. And so that is a statement that gravitational waves carry positive energy. And therefore, as Bondi said long time ago, because I told you that there was a confusion about reality of gravitational waves. So he said that, well, with this formula, the flux of energy is given by this gravitational energy. gravitational waves are real and they carry positive energy. So he said as a joke, but you can heat water with them if you want it. You'll have to be very close to the source for this to have enough energy to be able to heat water, but just in principle, it is true. Now, there are some commonly used formulae in the literature that I would like to now talk about. And the commonly used formulae in the gravitational wave literature are the following. Now, what I've done here is really invariant language, because somebody asked me in the very first lecture about coordinate invariance and so on. Everything here is invariant. We really don't need coordinates or even tetras, actually. If you just talk about D and lead C, and you talk about N's and such thing, I don't really need tetras or coordinates. In gravitational wave literature, particularly for numerical simulations and such thing, we often use coordinates, and therefore I would like to introduce this important notion, write down the same formulae in more coordinate language up here. So the expressions given above do not depend on any coordinates or tetras or pseudo tensors. At Scry, one can unambiguously calculate the fluxes of energy, momentum, and so on, and these are all covariant expressions. But one often introduces coordinates u, theta, phi, as we have done sometimes, to make expressions explicit. For example, for numerical simulations. One also defines an angular derivative operator in the theta phi direction. It is called eth. And that acts on what is called as spin-weighted functions or spin-weighted scalars. So I would like to introduce this terminology because you will see this a lot in the theoretical papers, numerical relativity papers on gravitational waves. So the statement is the following, that first let me tell you what is a spin-weighted scalar. So supposing you are given some tensor, like for example, our news tensor NAB, right? Or our tensor KAB, or our shear tensor sigma AB. You are given some tensor like that. What we can do is to take its component in the null tetrad, which is the M bar, L and N. And for the present purposes, what really is interested is just M and bar. And so supposing you look at those components, and if under MA goes to e to the I alpha times MA is a complex vector such that MA is equal to 0 and M bar A is equal to 1. So supposing we got MA goes to e to the I alpha MA, then this new MA, M prime A if you like, will also satisfy the conditions M prime A equal to 0 and M prime A, M prime bar, M prime A, M prime contraction, M prime A with M prime bar A is equal to 1. It will also satisfy that condition, just a phase factor up here. So supposing I made such a change in it is called a diode, M and M bar is called a diode, two vectors. Then supposing these components are such that they change by e to the S alpha, then we say that the spin weight is S. So it has a spin weight S if under the change of this diode rotation, it changes by this quantity. So for example, for our shear, which is M bar, it has spin weight -2, because and if M changes like that, then M bar will change with minus e to the -2i alpha. So this -2. So, and similarly, N has spin weight 2 because it only has M. Basically, spin weight counts how many M's it has minus how many M bars it has. And psi4 naught also has spin weight 2. Now, if A has if a scalar A has spin weight spin weight S, then the angular derivative, which is called f of this object, is just defined here explicitly. And the result up here has a nice property that again it is spin weighted. So it changes under this transformation, it will change by that, but it just adds +1 to the spin weight. So this was introduced by Newman et al. For certain Newman Penrose for certain calculations. This is the angular derivative called eth up here. And then in terms of this spin weighted quantities, then what we can do is we can go back to this formula that we had up here and write N in terms of its components, which are spin weighted, and write so N can be written in terms of this component. Remember, it was given by ln of sigma dot. So if I can put here mm bar, mm and m bar, I have components of n up here. And so the statement is that the formula that I had written before can just be given by the flux of supermomentum F times NA is given by this. This is the same as before. And what's happening up here is really that in place of NAB and NAB, I just get this form. I think I should write it in a form that is, okay, it is just given by this formula up here. So that the angular derivatives that are actually involved up here. And similarly, therefore, if I have the 4 momentum, then this term you can forget about it because of the fact that just like here, we can forget about this term because of the boundary gauge for a translation. This term vanishes, and therefore I am just left with this quantity here. So that is what I wanted to do today. And next time, what we're going to do is to start applying this. So what in the very first lecture, I told you that the plan has to do 2 parts. Part 1, which is conceptual and mathematical issues about gravitational waves. And I introduce the conceptual framework now. And the part 2, which is the next 2 lectures, we're going to use this in order to see how exact general relativity can be used as a diagnostic tools to test the accuracy of waveforms and to improve the waveforms. That is why I was asking the question about if people knew about those waveforms. And the answer I got was that no, people don't know about it. So I will introduce them next time. So please, do you have any questions? Either ask them on the phone, by unmuting yourself, or put them on the chat box.
There's a question in the chat box. It's by
I don't see it.
Sao Yu Yin. I will copy
two new messages. Okay.
Paste it again.
I don't see it here. Is there a message on the chat box?
Is there some type
Oh,
of
yeah. No. That was my question. Are you familiar with the waveform models? No, some other question. Oh, I see. Sorry. I learned optics and electron waves. No. Okay, I heard about. Oh, okay, so just ask me the question because I don't see it anywhere. Can you ask me the question orally?
Excuse me. Can you hear me?
Yeah, I can hear you.
Yeah, I wonder more about the introduce of the operator D. When you
the derivative operator, the derivative operator D, is that what you're talking about?
Yes, the operator D.
Okay.
When you write down,
okay, so
when you write down D, act on L, I'm confused because L is not tangent.
Very good. Thank you. Thank you for asking. Okay, thank you. Very good. Good. Okay. So, thank you. Good question. Oh, sorry. Yes. Very good. I got Scry here.
Yes.
And Scry is a null surface. So there are some counterintuitive things that happen in Scry.
Yeah.
So L as a vector
is
really not tangent to Scry, as you say.
Yes.
But if I look at L as a covector, then this is given by GAB times times LB, right?
Yeah. Yes.
And the statement is that as a covector, this object is a covector within Scry because this. So the tangent vectors to Scry are, if you like, an A, and and in the angular direction, MA and M bar B.
Yeah.
cotangent vector what are they? So you agree that scri is coordinatized by u and theta and phi.
Yes, I agree.
And therefore, if I just give myself scri, then I can talk about the vector which are d by du, d by d theta, and d by d phi.
Yeah.
So this vector is the vector NA that we talked about. And combination of these vectors give you MA and M bar A, as we've seen some time ago. Okay. But because you have got this in terms of covectors, cotangent vectors, I also have du, d theta, and d phi.
Okay, I see. Okay.
And these objects are precisely given by MA and M bar A. But this object is exactly LA, because remember LA and A, minus du is equal to LA, LA and A is equal to -1, and NA dA of U is equal to +1. So therefore, minus dA minus du is precisely LA. So LA is equal to minus du. So as a covector, LA is an intrinsic object defined just on scri.
Okay,
Covector.
okay, I know. Yeah.
Not as a vector. So you're completely right. I'm really happy that you asked me this question, because you're completely right that this object is not defined.
Yes.
But this object is well defined.
Yeah. Yeah, I see. Thank you.
Oh, very good question. Thank you for asking.